Hasan, and good evening to the participants who are watching this live session. So, ladies and gentlemen, esteemed colleagues and enthusiasts of space exploration, welcome to today's session on the yearly universe revealed by the James Webb Space Telescope. This session aims to explore the significant contributions of the JWST in enhancing our understanding of the yearly universe. So launched in December 2021, the James Webb Space Telescope represents a quantum leap in astronomical technology and capability. As the most powerful space telescope ever built, it serves as a successor to the Hubble Space Telescope, and it's designed to answer some of the most profound questions in astrophysics. In this session, we will discuss how the JWST's advanced instruments and its ability to observe in the infrared spectrum enable it to peer back over 13.5 billion years to observe the first galaxies that formed shortly after the Big Bang. This observation window into the cosmic dawn is a critical for understanding the formation and evaluation of the earliest structures in the universe. We will also cover how the JWST provides insights into the formation of stars and planetary systems, investigates the potential for life in other parts of the universe by examining the atmospheres of exoplanets, and helps in understanding the roles of dark matter and dark energy in the evaluation of the universe. Throughout this session, we will delve into the initial findings and the images provided by the JWST, discuss its technological advancements, and consider the implications of its discoveries for our understanding of the universe history and our place within it. This session is a journey through time and space, revealing the secrets of the early universe as uncovered by this remarkable observatory. So, before that, we start Dr. Hazima's session. I would like to give some short introduction about her. So, we are honored to welcome Dr. Hazima Hasan as our guest speaker. Dr. Hasan is a distinguished NASA program scientist overseeing pivotal projects like the Nuclear Spectroscopic Array and Imaging X-ray Polarimetry Explorer, the Keck Observatory, and the Astrophysics Data Curation and Archival Research Program. She also serves as the Deputy Program Scientist for the James Webb Space Telescope and holds key roles in astrophysics education and the advisory committee at NASA. Dr. Hasan ensures that each project aligns with NASA's strategic objectives and has contributed to numerous missions, including the Wide Field Infrared Survey Explorer, Hubble Space Telescope, and others. She earned her doctorate in theoretical nuclear physics from the University of Oxford and has a rich background in research and teaching. Her accomplishments extend to publishing in peer reviewed journals and receiving several prestigious awards and fellowships. Dr. Hassan's expertise and experience make her an invaluable contributor to our understanding of the universe. At the end, I would like to introduce to the motto of Dr. Hasma, exploring the cosmos, unveiling the mysteries of the universe with cutting edge technology. So I would like to hand over the session to Dr. Hazima, and also thanks a lot for joining us today, and over to you, ma'am.
Okay. Good morning and good evening. Thank you so much for that kind introduction. It's an honor for me to talk about a mission I worked on since its very inception, since it was conceived in 1989, actually, in a science conference. So if we could go to the next slide, the James Webb Space Telescope is a technological wonder. We think of it as the infrared, NASA's infrared eyes on the universe, with its 6.5-meter beryllium mirror, which consists of 18 gold-coated hexagonal segments, a tennis court-sized 5-layer Kapton sunshield, and 4 powerful instruments. It's already beginning to unveil some of the secrets of the early universe. The next slide shows uh, the the scientific objectives of the James Webb Space Telescope. It is designed to study every phase of the universe, starting from the end of the Dark Ages, when the first light from the stars penetrated the universe, formation of galaxies, the birth of stars and planets, and also about the the outer planets of our own sister system, as well as extrasolar planets. So let's go back quickly and look at the history of the universe. When the universe started in the Big Bang, when the entire mass and energy of the universe suddenly started expanding. It wasn't as though there was a big loud sound, but the sudden expansion has been named the Big Bang by the scientists. So in the first microsecond, the first particles, neutrons and protons were formed, and 3 minutes into it, the first nuclei of helium and hydrogen. But it wasn't till about 380,000 years later that the first atoms formed, and then 200 million years later that the first stars started forming, and then 400 million years later galaxies, and then 10 billion years later dark energy. So this is where we are today. So what James Webb is doing is going to look at really this first stars which were formed 200 million years ago. Sorry, after the Big Bang. So if you could go to the next slide, which slide are we on? Then yes, this slide. So so now you can see that the reason that we have to see in the infrared is because the first stars and galaxies, the light which left them as blue and ultraviolet has stretched. As the universe expanded, the light also stretched, and it has now reached us in the infrared. And it is that infrared light from the first stars that James Webb is going to study, is in fact studying. So if you could go to the next slide. Could we go to the next slide, please? So just to remind you where the infrared light is in the electromagnetic spectrum, as you can see, the visible part is really a very, very tiny part of the spectrum, which we can observe with our eyes. And the Hubble Space Telescope observes in the ultraviolet, visible, and a little bit of what we call the near infrared. And the Webb telescope observes from infrared right up to near infrared to the mid infrared. And the Spitzer telescope, which has stopped functioning now, this ended its operation, was from mid infrared to the far infrared. If we could go to the next slide, please. So another advantage of the infrared is that it peers through and examines the dust. So if you're looking at closer objects, such as stars which are closer to us, if you observe in the visible, the extreme left-hand side image is from the Hubble Space Telescope in the visible. So there are these dust columns which hide the newly born stars. But if you look in the near infrared light, which is the middle image, also taken by the Hubble, you can see that the infrared light penetrates the dust, and we can start seeing the newly born stars, not only from their own light, but the some of the dust that they're around them that is emitting the near infrared light. And on the right-hand side is a mid-infrared image taken by Spitzer Space Telescope, which detects the heat from the cooler objects, such as cool dust. And you can see the pillars of dust dissolving with the heat of the newly born stars. If you could go to the next slide, please. So let's start looking at some of the images of the of the Webb Space Telescope. So Webb is being used to re-examine a star birth, and here is a star-forming region referred to as Rho Ophiuchi, and this image allows us to witness a very brief period in the stellar life cycle with a new clarity that hasn't been available to us before. This image shows a region with approximately 50 young stars, and all of them are similar in mass to our sun or a little bit smaller. And the darkest areas are the densest, where the thick dust cocoons still forming protostars. So you can't see the stars which are behind that thick dust. And the huge bipolar jets of molecular hydrogen, which are represented in red over here, dominate the image, and these occur when a star first bursts through its natal envelope of cosmic dust and heats up, throws out these jets of hydrogen and lights them up with its light. And below it, and the lighter colored gas surrounding consists of polycyclic aromatic hydrocarbons. Next slide, please. Could we go to the next slide? Yeah. Here is another star-forming region. And these are stars which are actively forming, and this is called Herbig-Haro objects, and this is a pair of actively forming stars. And as the stars inject and eject gas and dust, the material is shot out into lobes on either side, which you can see in this image. And the bluish cloud that you're seeing in the image is known as a Bok globule, and it represents gas and dust through which you can see stars and galaxies. And over millions of years, these stars which we are seeing forming, the Herbig-Haro objects, they will become fully formed stars. So here we are actually seeing stars being born, which is really exciting. So could we go to the next slide, please? Webb has also observed the earliest, most distant stars, which was first detected by Hubble. And here you can see on the left-hand side is a galaxy cluster, and the inset in there, which marked by a square on the left-hand side and expanded on the right, is a massive galaxy cluster, which warps the fabric of space and time and produces a magnifying effect. So the galaxies behind this is magnified and appears like this reddish arc that you see over here. And this is known as the sunrise galaxy. And it is the most strongly magnified galaxy known in the universe's first billion years. Now, within this galaxy is the star Earndel, which is the most distant star ever detected. And this is a massive B-type star and is more than twice as hot as the sun and million times more luminous. And based on the colors of this star detected by Webb, there are hints of a companion star can be seen. And detecting stars closest in time to Big Bang can provide an insight into the early history of the universe. If we could go to the next slide, please. Webb has also seen the tiniest free-floating brown dwarfs. Now, brown dwarfs are objects which are, some scientists call it failed stars. These are bigger than planets, but smaller than stars, and they haven't lit up. The nuclear reaction hasn't taken place inside them to form them into stars. So here on the left-hand side, uh, in the image, these dots marked as 1, 2, and 3 are magnified on the right-hand side, and these have been identified as brown dwarfs, and they are 3 to 4 times the mass of Jupiter, and these are the smallest objects observed that can form in a star-like manner. And these brown dwarfs are cool, so therefore they emit infrared light and are detected by Webb. And 2 of the brown dwarfs show spectral features which are identified as hydrocarbon. And they are the same infrared signature detected by the Cassini spacecraft in Saturn and its moon Titan. So the questions that are under study from this observation is, how does star formation process operate at such very, very small masses? And are these actually brown dwarfs, or are they rogue planets? And the evidence so far is pointing that they're most likely brown dwarfs. But we need to expand our search area to understand these objects a little better. If we could go to the next slide. This is a view of a dusty disk surrounding a star called AU-MIC. And these infrared images provide clues to its composition. This system is one of very few examples of a young star where we know that exoplanets exist, and a debris disk that is near enough and bright enough to study holistically using Webb's uniquely powerful instruments. And the disk is brighter in the shorter wavelengths or bluer, which likely means that it contains a lot of fine dust that is more efficient at scattering shorter wavelengths. And importance of studying these dusty disks is that this is where planets are formed. So we hope to learn more about planet formation by studying these dusty disks. If we could go to the next slide, please. So here is a study of the only asteroid belts around that have been detected outside of our solar system. These are detected around the star Fomalhaut, which is about 25 light years away. And this was the first asteroid belt which was ever seen outside our solar system. And with Webb, we can see that this belt is more complex than the asteroid and Kuiper dust belts of our own solar system. And you can see on the left-hand side, 3 of the nested belts extend out to 14 billion miles from the star. And the inner belts have been seen for the first time, because in the earlier observations, there was just one, unresolved belt. So the dusty belts are debris from collisions of large bodies and analogous to asteroids in our comets. And you can see the inset has been blown out on the right-hand side in 2 different wavelengths, and so you can get a better understanding of this bright spot, which is a big dust cloud in the outer ring. And so studying these belts is important. It tells us about the debris around stars. Now we've been looking at the formation of stars. Let's look at death of stars. If you go to the next slide, this is something called a Wolf-Rayet star. Yeah, and these here you can see this is a star which is in its death throes. It's throwing out gas as it's dying. The image on the left is a near infrared camera image. And the one on the right is the same star taken in mid-infrared. So you see more of the dusty lanes over there. And the nebular structure is created by the material which is cast off from the aging star. And it is displayed by mid-infrared, on the right-hand side. This brilliant stage of mass loss precedes the star's eventual supernova, when nuclear fusion in the core stops and the pressure of gravity causes it to collapse in itself and then explode. So, that's how supernovas are formed, and we are beginning to see the early stages of that process. And so Webb will help astronomers to explore questions that were previously only left to theory about how much dust stars like this create before they explode as a supernova, and how much of that dust is large enough to survive the blast and go on to serve building blocks of future stars, planets, and complex molecules. If you could go to the next slide. So here are the remains of a star after it went supernova. This is called the Cassiopeia A supernova remnant, which is located at 11,000 light years from the Earth. So it's pretty close. And the image shows an expanding shell of material slamming into the gas shed by the star before it exploded. And so the tiny knots of gas, which are shown as orange and pink in the inner shell of the nebula, are comprised of oxygen, argon, neon, which come from the star itself. And they give a hint at how the dying star shattered like glass when it exploded. On the outskirts of the inner shell, it marks where ejected material from exploded star is ramming into the surrounding circumstellar material. And the light echoes in the bottom are from the light of the exploded star that is warming the distant dust, which is glowing as it cools down. So here we are seeing what happens after the star dies. So should we go to the next slide, please? So Webb is also seeking some of the first galaxies. This is Webb's first deep field, which was released by President Biden. And the astronomers are now beginning to study this deep field and find all the secrets in it. There are thousands of galaxies in here, which date back as far as like about 400 million years after the Big Bang. Next slide shows what an example of one of these. Should we go to the next slide? Yeah. So on the left side is the deep field, and there's a little inset marked yellow, which is then expanded on the right-hand side. This has been called the sparkler galaxy by the astronomers because of these little stars which are on which they have found on the around it. And the one with the little square in the green has been expanded, and that has been identified as a globular cluster. And globular clusters are important because these are the oldest stars which were formed. And these dense clusters which are seen here, they contain some of the universe's first stars. So as astronomers start studying the stars in these clusters, we will be learning more about how the very first stars were formed. So if you could go to the next slide. So this is a survey which is called the Cosmic Evolution Early Release Survey. And here you can see they examined the galaxies, and they estimated that these galaxies existed when the universe was 600 million to 6 billion years old. And the galaxies in the early universe are often flat and elongated. Now, this was a surprise. The early galaxies seemed to be like surfboards and pool noodles, and they were rarely round like volleyballs or frisbees. And these distant galaxies are also far less massive than nearby spirals and ellipticals. They are precursors to some massive galaxies like our own. So if we could go to the next slide. This is actually, if you could click on to the slide on the left-hand side, it's a movie, it's a video. Can you click onto the video? Left hand.
Ma'am, cannot access here. No.
Go a little lower and see. Click there. See if you can get the video to work.
No, ma'am.
Okay. Well, this was a video which it was a beautiful video which showed you like every second was equal to 200 million years, and the video flies through, showing the galaxies when they were, uh, uh, you know, up to when they were like 300 million years after the Big Bang. So you can see how the structure changed from the beginning till now. You're still not able to play the video?
Yes, ma'am. Cannot access here.
Okay, never mind. Okay, let's go to the next slide then. It's a beautiful video, so if you're able to see it, it'll be really nice. So Webb's spectra had reached a new milestone. So Webb, as I'll talk a little later about the instruments, but it has both imaging instrument cameras as well as spectrographs. And from the spectrographs, they have been able to measure galaxies which go back to about 300, 400 million years after the Big Bang. So on the left-hand side is a near camera image, and there are 4 galaxies which have been identified in this image, for which the spectra are taken, and the spectra are shown on the right-hand side. And the red line marks what is called the Lyman break. So it's known that in the rest frame of the galaxies, below this wavelength, it's absorbed by dust. And so this wavelength is known in the rest frame of the galaxy. So if you see how far this has moved in the infrared, you can determine how far the galaxy is. And from these measurements, the astronomers have been able to determine that these 4 galaxies date back to less than 400 million years after the Big Bang, when the universe was only about 2% of its current age. So we are really beginning to see the first stars and galaxies. Next slide, please. So here's a very interesting galaxy known as the Cartwheel Galaxy, which is well studied by other telescopes, but Webb is beginning to show some new features here. And we can see that this is a lab for star formation. It's formed by the impact of 2 galaxies, the one shown in red on the left-hand side on the top has gone through the galaxy on the right. And as it goes through it, as you can see, it causes a lot of commotion in there, and a lot of star formation is taking place. And this is a composite image of the near infrared camera and the mid-infrared camera. And the mid-infrared camera, you can see the cooler dust and the hydrocarbons which are forming. And the near infrared camera, the blue, orange, and yellow are what is seen with the near infrared, and the red is what is seen with the mid infrared. So you can see that also that the old stars are formed. Their distribution is more uniform, and it's in the center of this galaxy. And the new stars are formed in little tiny clumps all around the galaxy. And the the reddish arms, which are seen with the mid-infrared, are the dusty arms of the which are formed as these interactions take place. So, as this small galaxy passes through the big galaxies, there's a sudden, new star formation taking place, and we're getting insight into it with Webb. The next image is this is a collection of 19. Should we go to the next one? Yeah, this is a collection of 19 face-on spiral galaxies. And it's just very overwhelming and awe-inspiring. And here you can see the older stars appear blue here and are clustered in the galaxy cores. And the mid-infrared observations highlight glowing dust, showing where it exists around and between stars. And it appears in shades of red and orange. And the stars that haven't yet fully formed and are encased in gas and dust appear bright red. And the spherical shells in the gas and dust are visible in detail. And these holes may have been created by stars that exploded and carved out giant regions in the interstellar medium. The several galaxy cores are awash in pink and red diffraction spikes, and these are clear signs that these galaxies may have central active supermassive black holes or central star clusters. So you can see there's a rich information over here. And as I talk about colors in these images, I do want to emphasize that these are what we call false colors because we can't see infrared with our eyes. So to enable us to see with our eyes, these have been translated into colors we can see. So these are just such spectacular images with so much scientific information in them. The next slide. So Webb helps us also to find distant planets. The image on the right-hand side is a composite of images taken with the Keck telescope on the ground, which also was able to detect details. If you could go to the next slide. So Webb is also going to tell us about the atmosphere of the planets. And here is a simulation of the Earth's atmosphere. If we were to observe the Earth from far away with a telescope and measure its atmosphere with a spectrometer, this is what it would look like. And so this is what we are trying to do with Webb. Next image. Next slide, please. So Webb has already taken its first ever direct image of a distant world. And here you can see on the left-hand side. So it says these are coronagraphic image. A coronagraph is sort of something which shields the star. So it blocks off the light from the star. So then you can see the planets which are around the star. So there's an instrument, in the near infrared camera has the ability to put a coronagraph and block out the light so you can see planets around the star. So here is an image which Webb actually took of the stars. So this is something really remarkable, and hopefully we will be able to get more images. Next slide, please. Webb has also discovered its first rocky planet, and this is, again, it has done by measuring the light of the what we call the transit method. As the planet transits in front of the star, the light coming from the star gets dimmed. And here it shows the dimming of the light. And by measuring this dimming, one is able to measure the mass of the planet as well as its orbit. The spectra of the planet were also taken. And on the right-hand side, the white dots represent the spectra. And the green and purple lines represent simulations if the spectrum was composed of methane or of water. And I mean, uh, or of carbon dioxide. The green light, I mean, the green curve represents methane curve, the purple represents carbon dioxide, and the orange represents water and represents no atmosphere. And the data are more consistent with no atmosphere in this planet. But Webb has actually found has found many planets, but this particular planet with a rich atmospheric composition. The next one, please. The next slide. Yeah. So Webb has found this planet K218b, has measured the atmosphere of the exoplanet K218b, and it has found that it has a rich atmosphere which has methane, carbon dioxide, dimethyl sulfide, and that has been a very exciting find because dimethyl sulfide is usually given out by you know, it's a sort of a signature of life. So that's why this has been a very exciting discovery that maybe this planet has a life, and the detection of carbon and of methane and carbon dioxide and a shortage of ammonia supports the hypothesis that there may be a water ocean under a hydrogen-rich atmosphere. So we may have found a planet which could support life, but of course, a lot more study has to be done. Could we go to the next slide, please? So Webb is also being used to re-examine this our own solar system, the outer planets of our own solar system. So could we go to the next slide? So here is a Webb image of Jupiter, and we are beginning to see, and here we can see the auroras in the north and southern poles of the planet. And there are also, excuse me, and we are also seeing that the auroras shine in a filter that is mapped to redder colors, and they also highlight light reflected from the lower clouds and upper hazes. And the great red spot, which is big enough to swallow the Earth, this appears white in these views because it reflects a lot of sunlight. So we are beginning to get a lot of detail of Jupiter as well, and as of its rings and its moons. Next one. So Webb has studied Saturn's moon Titan, and Titan is an interesting object because it's a bit Earth-like. So with Webb and with the Keck telescope on the ground, we have been able to track the clouds over Titan, which gives us an insight on how air is flowing in Titan's atmosphere. And it's the only moon in our solar system with a dense atmosphere, as well as only place besides Earth to have present-day liquid rivers, lakes, oceans. And we hope to deepen our understanding of the Titan atmosphere. If we could go to the next slide. So here's one of Saturn's moon called Enceladus. And Webb has studied the water plume of Enceladus. So on the left lower side of the image, the inset, which is in the outer ring, is blown up here, so you can see a more detail of this uh, Enceladus water plume on the left-hand side, and on the right-hand side is a spectrum. And so the Webb instruments have revealed details into how Enceladus feeds water supply to the entire system of the planets. And these images show that water is, the plume is jetting from the southern pole of Enceladus and extends out to more than 20 times the size of the moon. And the Webb instruments have provided insights into how the water from Enceladus feeds the rest of the surrounding environment. And about 30% of the water actually stays within the torus, and the rest escapes to supply rest of the Saturnian system with water. So this is a new finding by Webb. If we go to the next slide, Webb has also studied Mars, and you can see on the top right-hand side is dominated by reflected sunlight, which reveals details similar to the visible image. So on the left-hand side is the image which was taken by the Mars rover, the Mars Observer instrument. And on the lower right-hand side is a Webb image, which shows thermal emission. And the brightest region is where the sun is directly overhead, decreasing towards the pole. And as the light emitted by the planet passes through the Mars atmosphere, some gets absorbed by carbon dioxide molecules. And the Heller Basin, which is the largest well-preserved impact structure on Mars, spanning more than 1,200 miles, appears darker than the surrounding because of this effect of carbon dioxide absorption. If we could go to the next slide. So this is my last science slide, showing the Webb's view of Uranus, which is a ringed world. And the Webb image exquisitely captures Uranus' seasonal north polar cap, which includes the bright white inner cap and the dark lane in the bottom of the polar cap. Uranus's dim inner and outer rings are also visible in this image, including the zeta ring, which is very hard to detect, and the extremely faint and diffuse rings closest to the planet. So you can see a lot of detail in the Uranus rings in this image. The Webb image also shows 9 of the planet's 27 moons, and they are shown as blue dots that surround the planet's rings. So this was, I hope I've given you just a bit of a flavor of the wonderful science that is coming out of Webb. So if we could go to the next slide. So how did the engineers make all this magic happen when the scientists said, we have these ambitious science goals, give us an instrument? So let's go to the next slide. So they came up with this brilliant idea that, to give a telescope with such a large mirror, we couldn't put it inside a tube the way you put in Hubble, because there was no rocket large enough to launch such a huge telescope. So they designed a telescope where the mirror is divided into segments. So the 18 hexagonal segments, and they can fold into themselves and then be put into the telescope. But then how was this telescope to be kept cool? Because it's an infrared telescope. We don't want its heat from its own elements to interfere with the infrared light that it's supposed to detect. So they said, let's put a huge sun shield under it, like a big umbrella, to shield the telescope from the heat of the sun and the earth and the moon. And so they designed the sun shield composed of 5 elements, and I'll talk a little bit more about it. And then there are 5 instruments: the near-infrared camera, which is provided by the University of Arizona. It's a NASA instrument. Then the European Space Agency provided infrared, and the NASA and ESA partnered to produce the mid-infrared instrument, and the Canadian Space Agency provided the fine guidance sensor and the near-infrared slitless spectrographs. So NASA partnered with ESA and CSA to enable this mission, because it's just too big and too complex for one agency to do it. So the design, if you could go to the next one, next slide. So this is what the design is, what is called a 3-mirror and astigmat. So there's the primary mirror where the rays come and hit the primary. Then they are from there they're reflected off a secondary, and then they go and hit a tertiary. So that corrects the some of the errors which are caused by the big mirror. And then there's a fine steering mirror, which then takes care of vibrations, and the rays which are focused go into the focal plane into the science instruments. So if you could go to the next slide. So Webb is really a feat of engineering. As you can see, this complicated telescope and its wonderful science instruments, a lot of new technology had to be invented. So if you could go to the next slide. So I won't mention all of them, but there were 10 really very challenging technologies which were invented between 96 and 2002. I've listed them here. I'm not going to talk about all of them, but what I will talk about are 2 of them, which was the primary mirror and the sun shield. So if you could go to the next slide. So the telescope mirror is fabricated from beryllium. So because of the properties of the beryllium, it has a low coefficient of thermal expansion, which means that the shape will not change as the temperature changes. As you've seen that the telescope has to be made very cold. So when it goes, it's warm, but then it has to cool down, and we don't want the shape of the mirrors to change. It has a high thermal conductivity, which makes it able to be uniform, and it's got a very high stiffness, so it won't break easily. And plus, it is very light. So you see on the image in the center, in the middle, is the back of the mirror. You can see the mirror is hollow, so that makes it light. And on the right-hand side is a full-size segment, and you can see the people holding it, gives you an idea of how big that segment is. And on the left-hand side, lower image, is the front of the mirror, which is polished, and before the gold coating was put on it. The reason a gold coating was put, because it has to reflect infrared light, and gold is a good reflector of infrared light. The next image, again, this is a video, and I don't know if you're able to play it. Could you go to the next image? The next one. Yeah, this is a video. See if you can play the video. You can't play the video?
Yes, ma'am, I can't.
Okay, well, this was a video which was showing how the robotics were used to integrate the flight telescope mirrors into the instruments. A very nice video. It is on the web. You can go and see it. But this is at Goddard Space Flight Center, which is where the mirrors were put together. What you're seeing here is the back plane on which the each segment was installed, and then it was installed one at a time, and then it was fully assembled, and then the instruments were put behind it. The next slide. Next slide shows that, so after the telescope was put together with the telescope and the science instruments, excuse me, it was sent from Goddard Space Flight Center in Maryland to Johnson Space Center in Houston, where they modified one of the chambers which had been used for the Apollo mission to test the optics of Webb. As many of you might know, a lot of people don't know this, that the mirror of the Hubble Space Telescope is flawed. So when Hubble was first went into space, the images which came back were blurry, and that had to be fixed at the next servicing mission. So we learned that lesson, and it was decided that the optics of Webb had to be tested. Hubble was launched on the space shuttle. It was possible to send a servicing mission to fix it. Webb is a million miles away. We don't have a space shuttle. There's no way we could fix it if there was a problem. So we decided it must be tested. So it was tested at Johnson Space Center in Houston. And here you're seeing it is emerging from the test chamber after cryogenic testing. Cryogenic means it had to be made really cold at the temperatures that it was designed to operate. If you could go to the next slide. So here's the other technology I wanted to mention is the 5-layer sun shield, which has an SPF of almost 10 to the power of 6, I mean, a million. And so it's composed of 5 layers, which are heat-resistant Kapton, which is coated with silicon on the sun side and aluminum on the other side. And it reaches a temperature of 85 degrees centigrade on the dark side and minus 233 degrees on the cold side. So there are like 7,000 seams of inches of thermal wells. And so it's really an amazing technology. Next one, again, is a video. I don't know if you can play the video. Can you click the image and see? No, it's not working for you. Anyway, this is again a video which showing the test of the engineering model of the sun shield. So it starts with the sun shield at the bottom, and then each layer is stretched out. And after all the 5 layers are stretched out, they are then separated. So this is also a very nice video. And again, it's on the web, so I hope you all will go and see it. Could we go to the next slide? Okay, so here is the what we call the optical element, which is integrated into the sun shield. So now here, so this is the actual telescope at Northrop Grumman in California. So you can see from the story I'm telling how many different places the telescope was assembled. And in fact, the parts came from, I think there are like 16 states in the United States, the different parts were manufactured in. It was assembled at Goddard Space Flight Center in Maryland. It was tested at Johnson Space Center in Houston, and then it went to the prime contractor, Northrop Grumman in California. They put it together with the spacecraft, and then it was, if you go to the next slide, it was sent for launch. And here is a cartoon showing how the telescope was folded up and placed into the nozzle of the rocket. The middle image shows how it was folded up. And on the left side, it shows that, how the nozzle is placed on the top of the rocket. And the rocket was provided by the European Space Agency. It's a French rocket Ariane 5. And the launch took place from Kourou, French Guiana in South America. Next slide. Here's a picture of the launch on December 25, 2021. And it took it into a perfect orbit to its final destination at a point called L2, Lagrangian point, where the uh, gravity of the Earth and the Sun and the Moon almost balance out. They don't perfectly balance, but they almost balance out. And so that's the point that Webb is orbiting. It's a good place for Webb because it can, it's far enough to remain cool, but close enough that we can communicate with it. And it's also in the right orbit to make all its observations. So that's extremely important. Next one. Again, this is a video. I don't know if it'll work for you. Can you see if it's working? No. Well, this was a video which shows the unfolding of Webb, how the different parts of it unfolded. So first, the high gain antenna comes out. Then the sun shields come out to provide the power. The solar arrays come out to provide the power. Then the sun shield comes out, and then the mirrors open out. And when the sun shield comes out, then one layer stretches, then the other, the 5 separate, and then the mirror comes out. Again, all these are available on the web. You can go and look at them over there. The next slide. So this shows where is the orbit of Webb. As I mentioned to you, it's at a point L2, which is 1 million miles from the Earth. The sun shield is always points towards the sun so that the telescope remains cool. So next slide, please. This is the command center for Webb at Space Telescope Science Institute in Baltimore, from where Webb is commanded. Next. And so the commissioning process of Webb took 6 months between launch and the first images. It had the deployments took place. The sunshine was deployed and the mirror was deployed as it was traveling to L2. So by the time it arrived at L2, it had been fully deployed. And then it had to cool down. So I think it took a couple of months to cool down to get to the right temperature. And then the alignment was done by the engineers at Space Telescope. And then the instruments had to be calibrated. So this entire process took 6 months. And when the first images were released, next slide, please. So these were the first images, which I'm sure all of you have seen. And on July 7, and then Webb was in operation, doing science. Next slide. So all the data from Webb is archived at the Mikulski Archives for Space Telescope. It's available to the public. Anyone can go analyze the Webb data. So any one of you who want to go analyze the Webb data, please go and analyze it. If you want to propose, the astronomers in the audience, if you want to propose your science to Webb, there is an open call for proposals. You send in your proposal. If it's selected, the telescope will point to whichever object you want it to point. If it's not selected, you can still get the data. Go to MAST and you'll get the data. And that brings me to the end of my talk. Thank you.
So, ma'am, thank you so much for your session.
My pleasure.
Yeah, ma'am, I have some questions here.
Mhm.
Yeah. How did the first galaxies form and evolve in the early universe? And what does this tell us about the process that shaped the large scale structure of the cosmos?
You know, your voice isn't coming very clear. Maybe you can put the
Yeah.
question in the chat as you're
Yeah, sure.
talking.
Yeah, okay. How did the first galaxies form and
Wha-
evolve in the early universe?
How did the first galaxies form? Huh?
Form and
Yeah.
evolve in the early universe.
And what?
And evolve in the early universe.
I didn't get the second part. So, how the first galaxies were formed is really what we are trying to understand. And, uh, uh, if you had been able to play a question,
I will send the chat box here.
I don't see anything in the chat box.
Yeah,
Okay, how do the first
yeah.
evolve in the how does this tell us
Ma'am,
about the
did you see that?
process that shaped large? Okay, how did yeah, and so it's pretty much as I said. This is an open question right now. It's very much. Any more questions?
Yeah, okay. Okay, ma'am, I would collect the questions. I will send the mail. Yeah, yes, ma'am. I would collect the questions and I will send you to the mail. Questions and I will send you to the mail.
Mm-hmm.
Hello?
What were the properties
Hello,
of the
ma'am?
first? Yeah, what were the properties of the first stars, and how did their formation and
Hello?
life cycle differ from stars in the modern universe? So you're asking very good
Yeah,
questions.
hello, ma'am. Did you see that?
Yes, can you hear me? Can you hear me? Can you hear me? Yes? Okay. So your question is, what were the properties of the first stars, and how did their formation and life cycle differ from stars in the modern universe? So these are really very good questions to which we don't have answers. That's exactly what we are looking for. And as I showed you some of the very first star that
Yeah.
or that has been observed, Erndel, we are studying that. We are seeing how stars are forming, and we we haven't yet seen the very first stars forming, but we've seen globular clusters, as I showed you in one of the images, which are the oldest stars. So these are questions which are still being studied. I don't think their life cycle is different from stars in the modern universe. It's the same life cycle, but by studying the earliest stars, we will learn about how the stars in the modern universe, how they will evolve. So I don't think the life cycle changes with the, how old they were, how they were formed. The process is the same. Any more questions? How can observation from JW contribute to understanding of dark matter and dark energy and their roles in the evolution of the universe? Ah, this is again, as I said, you're asking really good questions. These are all questions which are under study. We don't know the answers yet, but by but by beginning to learn about our uh, the first stars, first galaxies, and how they evolved, and and, and how they affect each other's motion. That's really what dark matter and dark energy, is we learn about, is when we see their impact on the objects around us, because we can't see them, but we can measure the impact on the objects around us. And with JWST, as we are getting more details and we are learning further back in time and we're seeing more things, we should be able to get a greater understanding of these unknowns. And who knows, we probably will find there are more unknowns out there we know nothing about. Because when Hubble was launched, we didn't even know about dark energy. So Hubble helped in the detection of dark energy. We didn't know about exoplanets, and then Hubble was has been able to detect and measure exoplanets. So there are going to be a lot of unknowns out there, which is probably the most exciting part of JWST. I find is the unknowns.
Yeah, okay. Thank you, ma'am. Thank you for the answers. The answers are very useful. I hope the access and the participants can understand about that. So, ma'am,
Yeah,
finally, so yes, ma'am. So finally, so ladies and gentlemen, as we come to the close of this enlightening session, I would like to extend our heartfelt gratitude to Dr. Hazima Hasan for her invaluable contribution. Dr. Hasan, your expertise and insights into the mysteries of the universe, as revealed by the James Webb Space Telescope and other groundbreaking projects, have not only enriched our understanding but have also inspired us. Your dedication to advancing space science and your role in overseeing some of NASA's most significant projects are truly commendable. The depth of your knowledge and combined with your ability to communicate complex concepts in an accessible manner has made this session both informative and engaging. We are grateful for the time you have taken to share your experience and finding with us. Your work serves as a beacon of inspiration of aspiring scientists and enthusiasts alike, reminding us of the vast possibilities that space exploration and research hold. On behalf of everyone here, thank you, Dr. Hassan, for your remarkable contribution to astrophysics and for playing a pivotal role in expanding the frontiers of our knowledge. Your efforts continue to the light the way in our quest to understand the universe and our place within it. So, thank you once again for a truly memorable and enlightening session. So, thank you, ma'am. Thank you so much.
thank you. I appreciate that.
Yeah, okay. Thank you, ma'am. Thank you so much.